Hello, and welcome to the first episode in the series on linear algebra. Today we're going to be covering something called a field. So what is a field? Well, a field is a set, and it's a set such that we have two binary operations. First binary operation is something called addition. So what this is what you generally know as addition, but we're just going to keep it there, keep it simple, and multiplication. We haven't actually defined what these are strictly, but for now just take it as what you actually know addition and multiplication to be. And we require our field to meet a set of axioms or rules. So the first axiom is it has to be an abelian group. So what that means is we take a set X, which has elements. These can be anything: paints, colours, numbers, integers, rational numbers. And firstly, we require, when you do a binary operation, such as, now this is just for addition now, when you do a binary operation, addition here, between two elements of the set, this has to be also a member of the set. Secondly, there should exist an identity element, such that when you add that identity element to another element, you get back the original element unchanged. So the identity element in the integers is 0, or in the real numbers it's also 0, because 0 plus 5 is equal to 5 plus 0, which is equal to 5. So this identity element has to be something called commutative, which means it doesn't matter what order I do the addition, I just should get the same result. So in this case is unchanged. Thirdly, under addition, our set has to have an inverse. So the natural numbers, the positive integers, do not have an inverse. So they're not a group under addition, but the integers do. Okay, so the natural numbers don't, the integers do. For the natural numbers, this inverse would be the negative. So I'll keep saying so. You take a number 1, you add its inverse, negative 1, and you get the identity element 0 again. That's that. So we've covered that, and finally, for under addition, we need the elements to commute, which means it doesn't matter what order you add the elements. So 5 plus 5 plus 4 is the same as 4 plus 5, which is 9. That's under addition. Secondly, it also has to be an abelian group, satisfy all those axioms when you take away the additive identity element 0. So when you take that away, it must be an abelian group under multiplication. Same as here. This means that it must be closed, so you take 5 and you perform multiplication on it. 5 times 6, that if they're both integers, then the result 30 must also be an integer. Secondly, there must be an identity element, so in multiplication this is 1. Thirdly, there must be an inverse in the real numbers or rational numbers. This is reciprocal. The inverse of 5 is a fifth. The inverse of 2 is a half, because when you perform that multiplication, you get the identity element, which is 1 under multiplication. And finally, they must commute. 5 times 6 must be equal to 6 times 5. So any element of the set, two elements of the set, under multiplication, as you know it, they must commute. Okay, so that's a quick, rough definition of what a field is. And I missed one important axiom out. This is distributivity. So this means when you take any triple ABC, 3 elements in the field F, we must have this fact. So when you have A and you multiply it by B plus C, you must be able to distribute, which you know in algebra is AB plus AC. This is because in algebra you've always been using your algebra, you've been using the field the real numbers. which means you've always been able to do this, but in some groups you can't do this. Sorry, in some vector spaces or some structures in maths, you can't do this. There isn't distributivity, but we require, under multiplication and addition, we require our set to have this rule that you can do this. An example is the real numbers, the complex numbers, and the irrational numbers. These include or whatever the normal numbers you can think of. There are more numbers, but they might not be a field. So numbers which structures which aren't fields would be, like I've already mentioned, the natural numbers. That's not actually a group, even a field. A group is a subset of a field. It's a weaker attribute. But yeah, so what isn't a field would be the whole numbers, the integers, because under addition they do have an inverse, and they're closed, and they have an identity 0, which is fine. But under multiplication, the integers don't have an inverse, because the inverse of an integer, well, that's not true. For one, that's true, but I'm talking about certain integers such as 2 or 3 or any integer not equal to 1. Remember, we throw out 0, so we can forget about 0, the inverse of 0. But if you take an integer such as 2 and you multiply it by another integer, there's no integer x such that 2 multiplied by x gives the identity under multiplication 1. And let me just remind you, 1 is the identity because when you multiply any element of the integers by 1, you get that element back. We all know that up to now, and it's taken as granted, but it's an axiom. A more abstract group would be the group which is just 2 elements, the element 0 and the element 1. Sorry, field, actually, not a group. It's a field and a group. So under addition, 0 and 0, 0, this is what we define it as. This is called the Cayley Table, and this is how you represent, or how you can create groups up to things called isomorphisms. So we have, under addition, 0 and 0, 0. This is what we define it as. This might be to you, it might be, yeah, of course I know 0 and 1 is 1, but this is our new group called F2. This is not the integers. So we define 0 and 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equal to 1, which is commutative, and 1 plus 1 equal to 0. And if you go up and you check all the axioms, distributivity, it is in fact a field. And the table for multiplication, if we throw away 0, we just get the simple trivial table, which is the singleton set 1. Okay, throw away 0, you get 1. And of course, 1 times 1 is equal to 1. That's closed. That's a member of our set, 0 and 1. It's commutative. 1 times 1 is equal to 1 times 1, and of course it's got an inverse. 1 times 1 is equal to 1, and the identity is 1. So it's very trivial. It's just one element, and that's just called the singleton set. So when we throw away 0 under multiplication, that is our field. And so that's what a field is. Okay, that is what a field is. In the next video, we'll cover what a vector space is and some propositions, and then we'll move on to the real core of linear algebra. Thank you for watching.